Okay, now that we have talked about exponential growth, it's time to do the opposite of that, which is exponential decay. So take a look at our learning goals. You can see that students will be able to recognize properties of exponential functions, apply exponential decay models, and graph exponential functions. Now, when we say that, you need to remember that each of these exponential equations are nothing more than y equals ab to the x. We talked about that a value being the initial value, the y-intercept. We talked about the b value being that growth factor. But now we got to remember growth could be a positive, which was our first section, and now a negative. We characterized it as an increase or a decrease. So growth is a word that actually has two meanings to it, and you got to keep that in mind. And then remember, the variable is to the power of x. So we're going to apply the exponential decay model, and we're going to graph exponential functions, similarly to how we did it with exponential growth. So knowing what we have here, let's move on and see how it's going to differ from the growth. So taking a good look, there's our equation again. Y equals ab to the x, where we said before, and it's going to hold true, that a cannot be 0 in either one of them. B cannot equal to 1, which is a true statement, because with b equal to 1, you're not going to have any growth whatsoever, or decay in that matter. So b cannot equal 1, true statement for both, and b cannot be 0. Meaning again, if a was not 0, b can't be 0 either, because 0 to any power would wipe the thing out also. So there's three things, characteristics that you can have for both of them. And if we go with this left side being the growth and the right side being the decay, you should be able to come up with a few characteristics that we've now talked about. So I want you to start this list, and we're obviously going to add to it and talk about it. So what could be one combination characteristic that you have? I'm going to start with, because a lot of you are visual, how about it has an exponential curve graph. Now, if it's a growth, we're going to draw a little picture next to it. Just to give you an idea, it starts low and goes high. Hugs that x-axis. We can say the same thing over here, exponential curve graph. And that now, this time though, we have that x-axis, and it starts high and goes low. So just the opposite or inverse. They both cross the y-axis at 1, so we could say that as a characteristic. Y-intercept equals 1. Oops. We talked about the b value being greater than 1 if it grows, so here's one difference. B has to be greater than 1 to be growth, where over here b has to be less than 1. Now if you want to be real specific, go back to those graphs that we have sketched there. You could say things like graphs into quadrant 1 and 2. Whatever that is. Same thing here. Graphs into quadrant 1 and 2. So there's characteristics, and we want you to think about them and add to these lists, because that's what we would like to talk about in class. All right? So give yourself a second to do that. Go ahead and hit pause. Add to your list before you move on to the next slide, seeing how many characteristics you could name. Things like, just because of the graph, you could do things like domain and range. as a possibility. Okay? So go ahead and hit pause and add a few more characteristics to your list. Now that you have those characteristics, let's look and see. I have a little more complete list on this next page and see how many of them we've talked about. All right, I just said talk about domain and range. So the domain, if we're talking about graphs that start low and go high, or start high and come low, are all real numbers. So if you look left to right, we're graphing all real numbers. The range is only in the positive reals. It never touches the x-axis, so it never hits 0. The y-intercept of each graph is that a value, that starting value. And on the graph we did on the last page, it was a 1. Graph never crosses the x-axis, true. And exponential curves have no x-intercept. So we sort of said that indirectly. In one of the two quadrants, the graph gets closer to the x-axis. Therefore, here's a new word for you, you will have an asymptote. And that asymptote's definition is a place where your graph appears to approach but never crosses, never touches. Then, the constant growth factor is greater than 1. As x increases, the value of the function decreases. So, as x gets bigger, y is getting larger. Exponential growth curve is the reflection image of the exponential decay curve over the y-axis. So if you took these two curves, and I don't know if I'll be able to draw them accurately, and drew the exact same combination in a decay situation, they would be reflection images of each other. So they would cross at the y-intercept same point. They would have symmetry to it. Okay? So probably these last two are things we didn't talk about, but now we know about in our inferred. So what kind of problems are we going to have? You're definitely going to have some decay or decreasing ones. So here's a real-world example. Some used car dealers use the rule of thumb that the trade-in value of a car decreases by 30% each year. So keep that in mind. As they say, the car isn't worth what you paid for it when you drive it off the lot. It is depreciating. This means that the car retains 70% of its value. So it's really growing by 70%. And 70% is a 0.7 as a decimal, so see why we say it's really decreasing. So here you go, in part A. You have a car worth $6,400. Write the equation that models, knowing we're doing exponential, that models the value of your car in X years. So here we go. We don't know our final price, but we do know its starting value is $6,400. And we know, according to our information, that it's growing by 70%, so 0.7 or 0.7d, your choice, same thing. And then it'll be raised to the power of x. Okay? So with that in mind, how much will your car be worth in 3 years? So in most cases, you would take your 6,400, times it by 0.7 to the power of 3, and you would find out that your car, after 3 years, is now worth $2,195.20. Wow, did it drop in value. But remember, it was only worth $6,400 to start with. And there you go. Now, you've owned the car for 2 years. How much was it worth when you bought it? Okay? So you're basically saying it's right now you have a value of $6,400, but we're saying we already owned it for 2 years. So this is a situation where we want to go back in time again. So the $6,400, the B value is still that 0.7 growth, but it's really not growing, it's depreciating. And since we owned it for 2 years already, let's go back and now change our exponent. And with that, we should be able to put that negative in, standing for back in time, and we should be able to find out how much we really paid for this car initially. And I've got $13,061.22. There we go. So back in time is always a negative exponent, and forward in time is the positive exponent based on, in this case, it was years. All right, that's all we have. Very similar to that growth situation. Now we have decay. Just be careful about what your B value is and how you're going to use it.